NormalNet, learning-based mesh normal denoising via local partition normalization. My name is Zhao Wenbo. I'm glad to introduce our work. Firstly, I will introduce the background of mesh denoising. Mesh is compressed by 3D points and edges that indicate the connection between points. Mesh can be classified by the source, synthetic, and scanned. Due to the limitation of scanning devices, mesh are inevitably contaminated by noise. Hence, mesh denoising becomes a necessary step in geometry processing. Most of the existing mesh denoising methods follow the two-stage approach, in which the face normals are denoised firstly, then the vertex positions are updated according to the denoised normals. The denoised normals can be obtained by manifold traditional methods, filtering-based, optimization-based, and similarity-based. However, a certain prayer cannot be guaranteed to always be effective to various kinds of noise. Thus, they failed on removing the noise on scanned meshes. Learning-based methods can solve this problem, but most methods directly organize the face normals as the input of a network, which the geometry information is discarded, leading to unsatisfactory results. To address this problem, we propose the learning-based method, namely NormalNet. The NormalNet follows the iterative denoising framework. During each iteration, firstly, the local partition normalization strategy is applied to the local structure around each face, which can transform the irregular structure into regular voxel representation. Then the voxels are fed to CNN to obtain the denoising normals. At last, the vertex positions are updated according to the denoised normal. Then I will introduce the method in detail. First, I present the pipeline of the local partition normalization strategy. Given a face, first the position and direction of the face is normalized. Then the space around the face is divided into dense voxels. At last, each voxel is assigned by the average face normals in it. Thus, both the geometry information and the normal information are persuaded. The representation is then fed to the network to obtain the normalized denoised normals. The network is made up of 3 residual blocks, 1 max pooling layer, and 3 FC layers. The output normals should be denormalized by rotation. Then the vertex positions are updated according to the normals. Since the mass structure changes after each iteration, we propose to use different network for different iteration. To generate the training dataset of each network, we propose an iterative framework. Give a set of noisy meshes and their corresponding ground truths. First, we select face and apply the normalization strategy on them. Then we find the corresponding ground truth normals as the targets, which is made up of a training dataset corresponding to the first iteration. Then we train a network on the dataset, and at last, the noisy meshes are denoised by the network, and we can select faces on the denoised meshes, which is corresponding to the next iteration. The performance of NormalNet largely relies on the training set. We will propose 2 strategies to generate a high-quality training set. First, considering that the number of feature faces and non-feature faces is significantly different, we divided the faces into several categories according to the maximum ground truth angle difference, and select the face from each category equality. Thus, the feature face and non-feature faces are balanced. Second, for the scanned meshes, the ground truth methods and the noisy ones are obtained by high and low precision scanners on the same objects. There exists a mismatch between the noisy meshes and the ground truth. To remove the mismatched faces, we apply filtering on the noisy meshes and remove the faces that have large difference to the ground truth. Then the experimental results are presented. We test our method on both the synthetic and the scanned dataset, and the denoising results are compared with several traditional schemes and linear-based schemes. Both the objective results and the subjective results will be shown, and the two objective metrics are employed: EA, the mean angular square error; EV, the L2 vertex-based mesh-to-mesh error. The objective results are shown in this table. 6 synthetic meshes and 4 scanned meshes are employed for evaluation. The proposed method achieves the best performance with respect to both metrics. Then we present the subjective results. Firstly, the denoising results of 3 sensitive modes are shown. It can be observed that in the first 2 modes, our method can effectively recover the features in the red box. For the last mode, which contains smooth surface, our mode can avoid introducing pseudo-features. At last, we present the denoising result of a scanned mode. In this work, all the noise on the synthetic modes are Gaussian noise. However, the noise on the scanned modes have different shape. The prior of the traditional methods are unsuitable to this noise, leading to bad results. Our scheme can learn the pattern of the noise and effectively remove the noise. Finally, I would like to summarize our contribution. We developed a novel learning-based mesh denoising method to persuade both the geometry information and the phase normal information. We propose the local partition normalization strategy to transform the local structure into regular voxels. Then we employ networks to obtain denoised normals. The proposed method outperforms other schemes in objective performance comparison and can persuade the feature while avoiding pseudo-features. That's all. Thank you for your attention.